Welcome back. In this video, we are going to begin discussing the last section of this chapter, section 8, on two variable inequalities. There's two pieces to this, and today we're only going to focus on the first piece, linear inequalities, which means a two variable inequality whose graph is a region of the coordinate plane bounded by a line. Solutions to linear inequalities are represented by shaded regions. All right, so you've seen these before, so that really shouldn't be anything new. But here our solutions are dealing with shaded regions instead of just the line itself. And again, we're dealing with shading, but it's also important to know the boundary. We're going to dash the boundary if it's not part of the solution. We're going to have a solid boundary if we are including it in the solution. So to graph these, first you need y equals mx plus b form. That's the best way that we know how to graph, so that's typically how we want to go about doing this. And from there, you want to actually graph the line. So use the y-intercept, use the slope to get more points, and from there you have to decide, dashed line or solid line. You use a dashed line if it's strictly less than or strictly greater than. So again, if it's not part of the solution, if the line itself is not part of the solution, you dash it. And again, that should equate to when we would use the open circle before for one variable inequalities. You want to use a solid line for strict or for less than or equal to and greater than or equal to. So that would mean that it is part of the solution, just like a filled in circle before. So that's kind of how you can relate it to your prior knowledge. And then you shade appropriately above for greater than or greater than or equal to, or underneath for less than. So let's dive right into our first example. It's already in y equals mx plus b form. So I start with my y-intercept, and then I have that slope of 3. So up 3 over 1, up 3 over 1. So there's kind of the basis of my line. Now once I fill in those couple points, I find the points, now I decide solid or dashed. So I look at my inequality sign. Now I'm going to say solid because of the or equal to. That or equal to piece means that my line should be part of my solution, and therefore should be a solid line. And then I look to see where the shading should go. Well, the inequality sign is saying less than. So less than equates to below my line. So below my line, start anywhere and kind of show, oh, below, that's going to be this region right here, that's underneath my line. Then you shade all of that, and that is going to be your solution region. All right, let's look at our next one. So here we have a y-intercept up at 1. Then we have a slope of negative 2. So down 2 over 1, down 2 over 1. We can go in the opposite direction as well. So there we get a general idea of the graph. But now I need to look at my inequality sign. So here it's strictly greater than. Strictly greater than means dashed. I'm going to dash that line. And then I see greater than. This time it's a greater than sign. And that equates to being above that line. So I just take it and I graph above my line. And then that's it. That is going to be my solution. All right, two more examples. So here, for this next one, that X one, remember this is a special line. Remember, that is a special vertical line that intersects with x equals 4. So that's going to intersect right there. And it's an absolutely vertical line. So now before I draw that line, I need to interpret here strictly greater than. Well, strictly greater than means my boundary is not going to be part of my solution, and I'm going to, in fact, shade my line. And then where is greater than? Well, this time is a little bit different, all right? So think of greater than. Well, where is greater than 4? Well, greater than 4 would be where x is 5 or 6 or 7. That's going to be over here. So for these unique cases where you end up with a vertical line, just think about where are the x values that are greater than 4? Well, they're going to be over to the right. So you have to sometimes do a little bit more thinking than just above or below when dealing with some of the special case lines. But otherwise, it's usually good to just think up or down, above or below. All right, well, what about this next one? Well, this equation isn't in y equals mx plus b form. So that means we're not quite ready to graph it yet. I have to get it in the form that I can actually graph it. So that's going to be my first goal, is to get it graphable. So I'm going to add my 3x over to my other side to cancel it from there. So I have 2y less than or equal to. The 3x and the 8 are not like terms, so I don't combine them. Then I divide everything by 2. And so there's the equation that I want to use. All right, so let's graph this out. Now that it's in a graphable form, let's actually perform it. So I'm going to start up at 4. 1, 2, 3, 4. I'm going to start there. Then I have a slope of 3 over 2. So up 3 over 2. Up 3 over 2. All right, and then you again want to keep that line going so you can be as accurate as possible. So I have it in slope-intercept form. So now let's look and analyze the inequality itself to see how the shading works. Less than or equal to. The fact that it is or equal to means I'm going to use a solid line. All right, so again, or equal to means solid, and then I see that it is less than. My y is less than that line. Well, where is less than that line? Well, less than is underneath, so that means I'm going to shade everything that is down here. And again, when it's solid, it means my boundary is part of my solution, along with everything that is being shaded. Another skill to have, along with being able to make a graph, is being able to work backwards. So look at a graph and write the equation that it came from. So I want to write an inequality that represents the graph below. I'm going to put it in slope-intercept form. And so the first thing I'm going to look for is the slope. So looks like I'm going up 3 over 1. Rise of 3, run of 1 would be a slope of 3. Excuse me. And then my y-intercept, where is it crossing the line? Well, it's crossing down at 1, or down at -1. I apologize. Once I have that structure, now I want to look to see about the shading. So everything that is underneath it is shaded. So that means I'm going to have less than, because it's shaded underneath. And it is dashed, so that means it is strictly less than. Okay, remember dashed means strictly less or greater than. So I'm just going to leave it like that, and that actually represents this inequality. How about the next one? Well, the next one, let's look at the slope. Down 1 over 1, down 1 over 1. So rise of -1 over 1, that's going to be a -1x, a -1 for my slope. And then where is it crossing the y-axis? Well, it's crossing the y-axis down at 6. So again, all I have to do is look for the slope, look for the y-intercept to make the skeleton of my inequality, and now I analyze. I'm shading underneath my line, so underneath means less than, and then it is a solid line, which means the boundary is included, which means I need the less than or equal to piece for that. All right, and then I have the inequality written, so I've solved that problem. Now let's move on to our last piece. Let's move on to the word problem really quickly to wrap up these notes. So you're going to the fair to go on the rides. You don't want to spend more than $15, all right? So we have $15, we can't spend more than that. Tickets are 25 cents each. Small rides require 3 tickets. Large rides require 5 tickets. So I'm going to let the number of small rides be my X, number of large rides be my Y. Because the question is how many of each can I go on? So that's what leads me to label my variables that way. Now, I'm making a money equation out of this. All right, we're talking about money. So I need to equate these number of tickets here to money. Well, 3 tickets, 3 times 0.25 would be 75 cents. 5 tickets, so 0.25 times 5 would be $1.25. So each small ride costs 75 cents, each large ride costs $1.25. So let's turn that into an equation. Well, remember, cost is the price times how many you have. So for small rides, the cost of going on small rides is going to be 0.75 times x. The price of one times how many you go on. For the large rides, same thing. The price times how many you go on. And you want your total cost. You want that cost to be no more than $15. So you could spend $15, you could spend less than $15, but you don't want to go over that amount. All right, now if we were to try to graph this, all right, in standard form, a way that you could graph this is by using the intercepts, all right? So I'm going to do that just to remind you of that skill, that way of graphing. So for the intercepts, remember for the x-intercept, remember the x-intercept is essentially removing the y piece from the equation. So you would just have 0.75x is less than 15. Okay, and I'm going to change it if we're finding the intercept. I'm just going to use equals. And then same thing for the y-intercept. So for the y-intercept, remember that's essentially taking out the x. So you would just have 1.25 is equal to the 15. You'll just have the y piece left. So if the x side divide by 0.75 you end up getting x is 20. All right, so let's plot that out. That would end up way here at the end. For the y, when you divide that out, you get 12, which would be that point right there. So again, when it's in standard form, sometimes the intercepts are a really powerful tool. All right. Now, less than or equal to, so that means we're getting a solid line because of the or equal to. Less than means we're going to shade underneath our line. So right here. Now, keep in mind, I'm only showing the first quadrant. Why would I only show the first quadrant? Well, because you can't buy negative tickets. All right. But I do want you to see how this works. So this is going to be small and large rides. So basically any point in there is an amount that I could do. So I could go on that many. Oh, 4 small, 2 large, and be within my budget. I could go in that point, that point. So you can list out possibilities. All right, any possibility that is in that shaded region is a legit amount that you could go on. So that's just what I want you to see in this real world context to a problem. All right, so again, lots and lots of good stuff today. So please make sure you go in, write that summary for me really quickly, and then come back ready to do your practice work.